Okay, so let us talk about transverse shear. So basically, it's a phenomenon you'll see. Like if we had beams like this, where we kind of just stacked three beams on top of one another and applied a force, if we didn't do anything to those, they'd kind of slide relative to one another. And the fact that they would do that sliding is going to reduce their stiffness. Whereas if we do something where we, say, bond them together with glue or fasteners of some sort, nails or what have you, then they're going to be stiffer. They're going to resist movement as much. But again, it's going to take some sort of force applied in order to resist that movement. So you kind of see it here. We got this engineering pad here. If I rotate this end here, you know, you can see how at the end we got all the sheets sliding relative to one another. Whereas if I just kind of clamp down on here to provide enough friction to resist the movement, they don't slide relative. They don't slide relative to one another, so it basically increases the stiffness at the end. So you get the same idea, you know, if you glued all those sheets together or even just put some staples through, they wouldn't be able to slide relative to one another, which means that they also they would be stiffer. So that type of behavior can also cause failure. So on the right here, we've got this example here where someone was applying a load. You know, it caused a shear load, and it caused failure kind of in the center of the beam there, amongst those links. So basically, you know, at the points where this wood here was kind of supposed to hold together, it didn't, and it's kind of caused it to split relative to those horizontal planes. So basically, you'll recall what we talked about for bending. We're going to get some sort of distribution of the force caused by that bending. So again, in this case, we've got a positive moment, so we're causing a compressive force at the top. So if we look at this little cube at the top here, and assume we're not in a pure bending situation, or assuming we're in a situation where the bending is changing over the distance of the beam because we have a shear load applied to it. In that case, if you know, say if we have a positive force applied on this end, negative force applied on this end, so that's going to be causing the bending moment to be growing as we move in the positive x direction. So in that case, that would mean that this force here is going to be a bit larger than, sorry, well, this stress distribution here is going to be a bit larger than this stress distribution here. So the overall forces are going to be a bit larger as well. So in order to counteract those forces, if we take that little cube, we're going to have some sort of shear force applied at the bottom that is basically large enough to counteract the difference between the forces caused by bending here and here. So as a result, this thing also isn't going to be in equilibrium. You know, the forces will be in equilibrium, but this will still have a tendency to rotate. So we need to add basically a bit of a moment couple here on these faces in order to prevent them from rotating. So, and again, this is kind of what we talked about when we kind of looked at you know, the forces on the cube that we're defining how shear how shear acts. If we zoom in really small enough, then basically you know, if we zoom into a tiny little amount here, tiny little amount here, then essentially if we zoom in enough, then it's small enough that there's no change in no actual change in the moment from one side to another. So in that instance, essentially the shear forces on that cube would be like this, with those values being equal. Because again, in this instance, we're kind of looking at a relatively large cube with at the top surface here. So at the top surface, obviously there's no shear because there's nothing there that can apply shear. It's just open air. But if we look at the cube, kind of a cube right below that, again, this cube has to have these forces applied to it, which means that the cube it is applying, when it has this force applied to it, that means that the cube below it has this force applied to it by that cube, which means that this force down here needs to be even so much larger. So essentially what happens is we end up getting the rate of change of the shear as we move kind of down from the top. It increases, and the rate of change is directly proportional to the to the stress caused by the moment there. So essentially, the rate drops until it hits 0 at the neutral axis, and then essentially it continues to drop, just becomes negative, and then which means that the shear stress drops down to 0 at the other end. Because obviously, if you have a cube at the top, there's no stress here at the top surface because there's nothing there. Same thing occurs at the bottom. So we want to go into some math on that. So if we take an arbitrarily shaped beam, it looks like an egg here, but if we take a tiny little slice of that thing, tiny little slice, up to a particular distance from the neutral axis, basically we're going to get a certain distribution of the force on either face of that based upon the stress. So on one side we're going to have this stress, we're going to call that sigma here. On the other side we're going to have another stress distribution, we're going to call that sigma prime. And those things are going to be slightly different because again there is some sort of shear force that is being applied that causes a change in the moment as you go about the x-axis. So that'll be dm there. So we're going to have a moment on this side, we're going to have that same moment on this other side plus a little bit. So that means that these forces are going to be a bit larger than this force, which means basically when we sum up the forces kind of in this direction, that those forces plus this force here caused by that shear stress on the bottom face here. So the shear stress times the area there, so that's the dx, the tiny little slice, and the thickness of the beam, that needs to be equal to 0. And then we just know how the stresses relate in terms of the moment applied, the y, and the I. So again, we can just take those, take that, plug it into these equations. That'll give us this. So again, we know that kind of the portion that's just due to the regular moment kind of cancels out. So we're left with the portion that is due to the differential in the moment and the portion that is due to the shear stress. So again, portion due to the shear stress, portion due to the differential moment. So we can just solve for that in terms of our shear stress. So our shear stress is 1 over IT times the rate of change of our moment over the length times this integral here of the y times the y times the differential of the little bits of area over the cross section integrated. So again, we know that this here is just equal to the shear force. We covered that a few lectures ago. So we can plug that into here. And this should also look familiar. So way back in lecture 7, we talked about the first moment of area. So basically, this integral here is equal to this area, the magnitude of that area times its centroid. Times the distance of its centroid to the neutral axis. So that should be familiar. We called that Q. We're still going to call it Q. So Q is just equal to the y bar times the area. So, and we can from there we can figure out what the shear stress is in terms of the load. It increases directly with the load times the Q times the I and times the T. So again, I and V are constant for the cross section. T will kind of vary based upon based upon the height. So basically, if you're looking at if we're looking at this here, if we're looking at the little top here, then it'll have a different T than if we were looking down at the bottom here. And then obviously Q varies based upon what height we're looking at as well, because we're looking at the Q for the cross-sectional area that is separated from the neutral axis by the kind of space you're looking at. So if we had just a rectangle here, and say here was our neutral axis, if we were looking at trying to figure out what the shear stress would be across this cross section, and basically we'd be calculating the Q. We'd be calculating the Q based upon this area and its distance, its y bar, from the neutral axis. And likewise, so we'd also be using the T for that. In this instance, it was a rectangle, so the T is constant. So we'll kind of look at we saw this this beam that has three things tied, glued together. So how does that? What sort of shear stress would be induced kind of at the point where those beams are glued together? So let's say we have something like this. So I'm just calling H being the height of just one of those. And we're trying to figure out what the stress would be here at that plane. So we would need to be determining the Q for this area up here, shaded in green here. So in that instance, again, Q is the area times the y bar. So the y bar here would be h, half h plus another half h. The area, that's going to be h times t. So Q just ends up being h squared times t. Got our I. So again, we talked about how for rectangular cross sections, the I is the base times the height cubed over 12. So again, in this instance, I used like the height. You use the overall height. So again, 3h here. So T is our base. 3h is the height for the overall cross section. So T times 3h cubed over 12. That gives us 9th cubed over 4. And then we take those two and plug them into this equation, and some stuff cancels out, and that gives us a stress of, at this point, of 4v over 9th. So yeah, not too difficult there. One concept that is also important is the concept of shear flow. So basically, if we take the shear stress that we calculate and multiply it by the thickness, so multiply it by this distance here, then that basically gives us a force per unit length of the beam. So kind of per unit length along here that would need to be resisted. Some sort of shear force per unit length. So that can be used to basically figure out. It's mostly used to figure out if you have a beam that's built up by separate members and you're using fasteners to attach them. So that would basically allow you to figure out, say, if you had a beam that you're applying some sort of, you made up out of two 2x4s that you nailed together, and if you ended up calculating your shear flow as being, say, I don't know, 1,000 newtons per meter, and you had nails that were each able to resist, I don't know, easily resist 100 newtons in shear force, then you could figure out that based upon that, you would need to apply those nails every you need to apply 10 of those nails per meter, which means you'd need to basically apply one every 10 centimeters. So so basically you can use that for different configurations. It's not just for horizontal cross sections as well. So if you have a beam like this in the middle here, you're still going to get shear kind of induced. That's going to cause this beam member here to slide relative to these beams. And you would basically just calculate the shear flow or the shear force that would be induced based upon using a Q of this area and this Y bar. In each instance, you still use the overall I of the entire cross section, and the V obviously is at that particular cross section. So that would be basically how much as well the number of cross sections that you're looking at come into play here as well. So basically, if you're this gives you the overall shear flow that would need to be resisted to hold this thing in place. So if you're holding it in place with just one kind of set of fasteners, that'll give you how many allow you to figure out how many fasteners you need for that line. If you're using, in this instance, say two sets of fasteners, then basically for each set of fasteners, you divide that by 2, and then same here. If this this formula gives you the shear flow that you need to resist overall, and then then you divide it by 3 to give you the shear flow that needs to be resisted per each set of 3 fasteners that you're using. So yeah, we'll do an example here.